Hello, this is Serene from Exam Hub Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2 Variant 1 October-November 2017. Question number 1, Part A. The drag force acting on a sphere moving through a liquid is given by the expression where K is a constant. This is the density of the liquid. And V is the speed of the sphere. Determine the SI base units of K. So K is equals to drag force divided by density into speed square, where the drag force has a unit of kilograms meters per second square. Density is kilograms per meter cube, and speed square is meter square per second square. Kilograms and kilograms gets cancelled. S minus 2 and S minus 2 gets cancelled. Hence the SI base units for K is meter square. Part B. A ball of weight 1.5 newtons falls vertically from rest in air. The drag force acting on the ball is given by the expression in A. The ball reaches a constant terminal speed of 33 meters per second. Assume that the upthrust acting on the ball is negligible and that the density of the air is uniform. For the instant when the ball is traveling at a speed of 25 meters per second, determine the drag force on the ball. So this ball, which has a weight of 1.5 newtons, falls vertically with initial velocity 0 meters per second at a speed of 25 meters per second. The drag force at that point is going to be equal to the constant K into density of the air into speed square. Since we don't have the values for K and density, we are first going to take this instance into account when ball reaches terminal velocity with a speed of 33 meters per second, just to get the value of K into density of air. So when the ball reaches terminal velocity, the drag force must be equal to the ball's weight. So 1.5 newtons of drag force divided by the speed square, speed of 33 meters per second, so square, is equals to constant K into density. So this leaves us with a value of K into density as 1 by 726. Now to calculate the drag force when the ball's velocity is 25 meters per second, we'll use our formula K into density, which is 1 by 726 at the speed of 25 meters per second, should square it, and hence we get a drag force of 0.86 newtons. Part 2, the acceleration of the ball. Okay, so for the instant when there is a drag force of 0.86 newtons and constant weight, the ball's acceleration is going to be the resultant force divided by the mass of the ball. The resultant force is going to be due to the ball's weight, that's 1.5, minus the drag force, that's 0.86, and the mass of the ball is going to be equal to weight divided by the 9.81. This is the acceleration. So the ball's acceleration is going to be equal to 4.18 meters per second square. Part C, describe the acceleration of the ball in Part B as its speed changes from 0 to 33 meters per second. Okay, so the initial acceleration of the ball is going to be all due to acceleration of free fall, that's 9.81 meters per second square. But with time, since air resistance in this question is not negligible, the drag force is going to increase with time, which reduces magnitude of resultant force, which in turn reduces acceleration. So when the ball reaches the terminal velocity of 33 meters per second, the ball moves with 0 acceleration. So 3 marks. Each of it will be credited to each of the points that you mentioned here. So we can write that initial acceleration of the ball is due to G. Second point would be acceleration decreases with time, since air resistance will start to increase, the drag force will start to increase, and this will reduce the magnitude of resultant force. And a time will come when the ball reaches terminal velocity, which means that upward force acting on it is equals to the downward force that acts on it, so weight will be equal to the drag force, and it will no longer be moving with any acceleration. So acceleration is 0 at terminal velocity. Question number 2, the variation with time t of the velocity v of two cars P and Q as shown in figure 2.1. The cars travel in the same direction along a straight road. Car P passes car Q at time t is equals to 0. Part A, the speed limit for cars on the road is 100 km per hour. State and explain whether car Q exceeds the speed limit. Okay, so the maximum speed that car Q reaches is 30 meters per second, which we must convert to kilometers per hour. So to convert 30 meters per second to kilometers per hour, we need to divide 30 by 1000. And since this is per second, so divided by, we need to convert seconds into hours, so 1 divided by 3600, and this leaves us with 108 kilometers per hour speed. And the speed limit on the road is 100 kilometers per hour, and car Q has reached a maximum speed of 108 kilometers per hour. So yes, it is over speed limit. So 30 meters per second is equal to 108 kilometers per hour. Car Q is over the speed limit. Part B, calculate the acceleration of car P. So car P's initial speed is 20 and its final speed is equal to 24 meters per second, and this change in velocity took place with an interval of 12 seconds. So final velocity minus initial velocity divided by the time taken, and that's 0.33 meters per second square of acceleration. Part C, determine the distance between the two cars at time t is equals to 12 seconds. So going back to figure 2.1, at t is equals to 12 seconds, car Q has covered a distance which is equal to area under the graph of car Q. Similarly, in the case of car P, this is going to be the distance that it has covered in 12 seconds. So car Q has traveled a distance of half into the base into height, and that is equals to 180 meters. Car P has covered a distance of half into height into sum of parallel sides, since area under the graph of car P's slope is a trapezium. So this is 20 plus 24. This leaves us with 264 meters. So car P has covered a distance of 264 meters at t is equals to 12 seconds, and car Q has covered a distance of 180 meters. So the difference is going to be of car Q is 180 meters, car P is 264 meters. Difference in distance is going to be of 84 meters. Part D, from time t is equals to 12 seconds, the velocity of each car remains constant at its value at t is equals to 12 seconds. Determine the time t at which car Q passes car P. So let's draw a new graph where car Q travels with constant acceleration until time t is equals to 12, and its final velocity is equals to 30. This is car P. Car Q starts to travel with initial velocity 20 meters per second, and it reaches a final velocity of 24 meters per second over a course of 12 seconds. So, and the question says that from time t is equals to 12 seconds, the velocity of each car remains constant. They continue traveling with constant speed at t is equals to, with whatever speed they had reached at t is equals to 12 seconds. So for next few seconds, car P will continue traveling at 30 meters per second of speed, and car Q will travel at 24 meters per second of speed. So for first 12 seconds, car Q has traveled 180 meters, which I'll mention here. Car Q has traveled 180 meters for 12 seconds, and car P has traveled 264 meters. After 12 seconds, they both are now traveling at constant speed. For car Q to catch up with car P, it should have traveled the exact same distance by that time as car P. So 180 meters, which it travels when it was accelerating at a constant rate from initial speed 0 to final speed 30, plus the extra distance that it covers when now it is traveling at constant speed. So extra distance is going to be equals to 30 into the time interval which travels for at a constant speed. This should be equal to the car P's distance when it was accelerating at a constant rate from 20 meters per second to 24 meters per second, and it had traveled a total distance of 264 meters, plus the extra distance that it now is traveling with constant speed. So that will be equal to the constant speed that it is traveling with, 24 into the extra time that it takes for it to travel at constant speed. When you have equated them, you will get a value of t as 14 seconds. These are the few more seconds after which car P and Q must have traveled equal distance. So in total, from t is equals to 0, we are going to have 12 plus 14, and that's equals to 26 seconds for car Q to pass car P. So t is equals to 26 seconds. This is the amount of time which it takes car Q to pass car P. Question number 3, part A, state the difference between a stationary wave and a progressive wave in terms of the energy transfer along the wave. So energy is not transferred while it is in a progressive wave. Part 2, the phase of two adjacent vibrating particles. So in a stationary wave, as long as there is no node between two particles, they are in phase, but in a progressive wave, particles do have a phase difference. So particles are in phase in a stationary wave. But we are only talking about the two adjacent vibrating particles, not all particles. Part B, a tube is open at both ends. A loudspeaker emitting sound of a single frequency is placed near one end of the tube as shown in figure 3.1. The speed of the sound in the tube is 340 meters per second. The length of the tube is 0.6 meters. A stationary wave is formed with an antinode at each end of the tube and two antinodes inside the tube. Part 1, state what is meant by an antinode of the stationary wave. So an antinode is a point where amplitude is maximum. Part 2, state the distance between a node and an adjacent antinode. So there are 4 antinodes, 1, 2, 3, and 4, and 2 adjacent antinodes are what distance apart? So 0.6 meters in total it takes for 4 antinodes. So these 2 antinodes, they are 0.6 by 3, that is equal to 0.2 meters apart. So 0.2, this is also 0.2, and this is also 0.2. This makes up 0.6 meters of length of the tube. So 0.2 meters is the distance between 2 adjacent antinodes, and distance between adjacent node and antinode is going to be half of it. So 0.2 divided by 2, that leaves us with 0.1 meters. Determine for the sound in the tube the wavelength. Distance between 2 adjacent antinodes is 0.2 meters, and that is always half of the wavelength. So lambda by 2 is equals to 0.2. So the wavelength that forms in the tube is of 0.4 meters. Okay, the frequency. So frequency is equals to speed of sound in air divided by the wavelength that forms. Speed of sound in air is equals to 340 meters per second, and the wavelength that forms in the tube is 0.4 meters. So 340 divided by 0.4, that is 850 hertz. Part 4 is determine the minimum frequency of the sound from the loudspeaker that produces a stationary wave in the tube. So the minimum frequency means the longest wavelength in a tube that is open at both ends in this question. So a waveform like this forms where this tube has got only 2 antinodes, this point and this point, on both ends. Length of the tube is still 0.6 meters. But only lambda changes. Here 0.6 meters is equal to lambda by 2, since distance between two adjacent NT nodes is lambda by 2. So the longest wavelength that could form in this tube is equal to 1.2 meters. So the minimum frequency of the sound that could be produced in this tube is going to be equal to the speed of sound in air, that is 340 meters per second, divided by the longest wavelength that could form in this tube. It's 1.2 meters. So the minimum frequency is 283.3 hertz. Question number 4 defines strain. So strain is extension over original length. Part B, a wire is designed to ensure that its strain does not exceed 4 into 10 to the power of negative 4 when a force of 8 kilonewtons is applied. The Young modulus of the metal of the wire is 2.1 into 10 to the power of 11 pascals. It may be assumed that the wire obeys Hooke's law. For a force of 8 kilonewtons, calculate for the wire the maximum stress. So stress is equal to Young modulus multiplied by strain. The Young modulus of this wire is 2.1 into 10 to the power of 11, and the maximum strain is 4 into 10 to the power of negative 4. So the maximum stress is equal to 8.4 into 10 to the power of 7 pascals. Next is the minimum cross-sectional area. So stress is equal to force divided by cross-sectional area. So the minimum cross-sectional area is going to be equal to force, the maximum force that's applied, that is 8 kilonewtons. So 8 into 10 to the power of 3 divided by the stress, the maximum stress of the wire. That's 8.4 into 10 to the power of 7. Hence the minimum cross-sectional area of the wire needs to be 9.5 into 10 to the power of negative 5 meters square. Question number 5. 3 cells of electromotive forces E1, E2, and E3 are connected into a circuit as shown in figure 5.1. The circuit contains resistors of resistances R1, R2, R3, and R4. The currents in the different parts of the circuit are I1, I2, and I3. The cells have negligible internal resistance. Use Kirchhoff's laws to state an equation relating part 1, all the currents I1, I2, and I3. Okay, so since E2 and E1, they're having their positive terminals facing each other, so their currents will be carrying a positive charge. So I2 plus I1, and E3 has its negative terminal facing the positive of E2 and E1. So the current across E3, that's I3, is going to carry a negative sign, that's negative I3, and this all should be equals to 0 because charge must be conserved according to Kirchhoff's first law. So the relationship is I2 plus I1 is equals to I3. Part B, E1, E3, R1, R3, R4, I1, and I3 in loop W, X, Y, Z, W. So electromotive force at this battery E1 is going to be equal to the voltage across R1, that's R1 and I1. And E3 is going to be equal to the voltage across R3 and R4. So current multiplied by the sum of R3 and R4. As both cells E1 and E3 have their opposite terminals facing each other, so we are going to have their sum E1 plus E3 is equal to whatever they were equal to. So R1 I1 plus I3 and the sum of R3 and R4. Part C, E1, E2, R1, R2, I1, and I2 in loop YZWY. So E1 again is R1 and I1, and E2 is equals to I2, R2. Since both cells have same terminals, positive and positive, facing each other, so we are going to have the difference between them. So we'll subtract E1 and E2. So E1 minus E2 is equals to R1 I1 minus R2 I2. Question number 6, define electric field strength. So this is force per unit positive charge. Part B, two parallel metal plates in a vacuum are separated by a distance of 15 millimeters, as shown in figure 6.1. A uniform electric field is produced between the plates by applying a potential difference between them. A particle of mass 1.7 into 10 to the power of negative 27 kilograms and charge positive 1.6 into 10 to the power of negative 19 is initially at rest at point A. On one plate, the particle is moved by the electric field to point B. On the other plate, the particle reaches B with kinetic energy 2.4 into 10 to the power of negative 16 joules. Calculate part 1, calculate the speed of the particle at point B. So the kinetic energy is equals to half into speed square, where kinetic energy of the particle is 2.4 into 10 to the power of negative 16 is equals to half into mass is 1.7 into 10 to the power of negative 27 into speed square. So the speed of the particle at point B is equals to 5.3 into 10 to the power of 5 meters per second. Part 2, state the work done by the electric field to move the particle from A to B. So work done in moving the particle from A to B is equals to gaining kinetic energy. So this is also equals to 2.4 into 10 to the power of negative 16 joules. Part 3, use your answer in part 2 to determine the force on the particle. So work done is equals to force multiplied by distance moved in the direction of the force. So the work done in the previous part we got is 2.4 into 10 to the power of negative 16. The amount of electric force is unknown, and the distance it moves from point A to point B is 15 millimeters. We need to convert that to meters. So 15 into 10 to the power of negative 3. And hence the force that is exerted on the particle is of 1.6 into 10 to the power of negative 14 newtons. Part 4, determine the potential difference between the plates. Now, since we know the electric force that's exerted on the particle, its charge, and the distance between the charged plates, we can equate the equations. So we can equate that the electric force divided by charge is equals to the voltage divided by the distance between the charged plates. The force is 1.6 into 10 to the power of negative 14. The charge of the particle is equal to 1.6 into 10 to the power of negative 19. The voltage is what we have to calculate, and the distance is 15 millimeters, so 15 into 10 to the power of negative 3 meters. Hence, the potential difference between the plates is 1500 volts. Part 5, on figure 6.2, sketch a graph to show the variation of the kinetic energy of the particle with the distance x from point A along the line AB. Numerical values for the kinetic energy are not required. So let's go back to figure 6.1 and see what happens with kinetic energy as the particle moves along the path AB. So with increase in distance between the particle and point A, speed of the particle will increase obviously, and so does kinetic energy. According to the formula, kinetic energy is equals to half mv square, where speed square is directly proportional to kinetic energy, which shows that speed does not share linear relationship with kinetic energy. But if we take kinetic energy in terms of distance, so this would become kinetic energy is equals to half into mass, where v square will turn into u square plus 2as. Now you can see that kinetic energy and the displacement from point A, they share a linear relationship because kinetic energy and s both are to the power 1. So the graph is going to be a straight line from origin because the particle starts to move from initial speed 0. So kinetic energy and displacement s from point A, they share a linear relationship with 0. So the graph will start from 0 and it will reach a maximum kinetic energy at x is equals to 15 millimeters. Question number 7, define the ohm. So they're asking you to define the unit ohm. That's of resistance. The resistance is voltage divided by current, so it's going to be volt per ampere. Part B, wires are used to connect a battery of negligible internal resistance to a lamp as shown in figure 7.1. The lamp is at its normal operating temperature, some data for the filament wire of the lamp and for the connecting wires of the circuit as shown in figure 7.2. Part 1 showed that the resistance of filament wire by total resistance of connecting wires is equals to 1000. So resistance is equals to resistivity into length by cross-sectional area, where cross-sectional area is equals to pi d squared by 4 in terms of diameter. So R becomes 4 resistivity into length by pi d squared. Now resistance of filament wire is equals to according to figure 7.2, it is equals to 4 into the resistivity of filament wire into its length divided by pi d squared, and that of connecting wires is equals to 4 multiplied by their own resistivity, that's 0.028 resistivity into the length, total length of the connecting wires, that's 7L according to figure 7.2, divided by pi into diameter square. The diameter is of 14D, so the whole square. Now the ratio of the resistances is going to be equal to 4 into resistivity into length by pi d square multiplied by pi and 14D square divided by 4 into 0.028 resistivity into 7L. So this leaves us with a ratio of 1000. Part 2, use the information in part 1 to explain qualitatively why the power dissipated in the filament wire of the lamp is greater than the total power dissipated in the connecting wires. So power dissipation is equals to I square R. The ratio of resistance of filament wire by resistance of connecting wires is 1000 by 1. So for every 1 ohm of resistance of connecting wires, there is 1000 ohms of resistance of filament wire. So resistance of filament wire is much higher than that of connecting wires, hence its dissipated power is also greater than that of wires, but the current stays the same. So we can write that power is I square R. Resistance of filament wire is higher than that of connecting wires. So power and resistance, they are directly proportional. When resistance increases, power dissipation will increase too. So this is the reason why the power dissipated in the filament wire of the lamp is greater than the total power dissipated in the connecting wires. You also need to mention that current stays same, because then only power dissipation will have a higher magnitude this time. Part 3, the lamp is rated as 12 volts, 6 watts. Use the information in part 1 to determine the total resistance of the connecting wires. So power dissipation is equals to V squared by R. So resistance of lamp, first of all, is going to be 12 square by the power, and that is equals to 24 ohms. Now the ratio of resistance of filament wire by total resistance of connecting wires is equals to 1000. This means that the resistance of the filament wire, which is 24 ohms this time, divided by the total resistance of the connecting wires is equals to 1000. So this leaves us with the total resistance of connecting wires as 0.024 ohms. Part 4, the diameter of the connecting wires is decreased. The total length of the connecting wires and the resistivity of the lamp of the connecting wires remains the same. So the diameter is going to decrease. State and explain the change, if any, that occurs to the resistance of the filament wire of the lamp. So this way, resistance of connecting wires would increase by 4 times, because resistance is inversely proportional to d square. When diameter decreases, resistance will increase by 4 times, which decreases the current across the circuit. When current decreases, voltage across filament wire will decrease, and hence its resistance will decrease. So we can write that resistance of connecting wires increases and current decreases. When current decreases, the amount of PD, that is across filament wire, will decrease, and hence the resistance of the filament wire will decrease too. PD across filament wire decreases, thus its resistance decreases. Question number 8. A neutron within a nucleus decays to produce a proton, a beta minus particle, and an electron antineutrino. Part A uses the Carb composition of the neutron to show that the neutron has no charge. So a neutron is made up of two down quarks and an up quark, where the charge of a single down quark is -1/3e, and a charge of an up quark is 2/3e, positive 2/3e. So this gives us an overall charge of 0. Part B, complete figure 8.1 by giving appropriate values of the charge and the mass of the proton, the beta minus particle, and the electron antineutrino. So the charge of a proton is positive E, charge of a beta minus particle is -e, and antineutrino does not carry any kind of charge. The mass of the proton in terms of kilograms is 1.6 into 10 to the power of -27 kilograms. That of beta minus particle is very low, that is 9.1 into 10 to the power of -31 kilograms, and antineutrino has a negligible mass or 0 mass. So that was the end of the paper. Thank you for watching.